everyone, welcome to this video on implicit differentiation. In this video I'm going to go through just a few examples of how this works and I guess why it works as well. There's a couple of key ideas that we need in order to be successful in this topic. So the first one is to have an awareness of the chain rule. If you're not familiar with that one yet, I'll just write it over here. It was that dy dx is dy du multiplied by du dx. In summary, basically what we do with the chain rule in order to differentiate is we differentiate the thing normally and then multiply by the derivative of the inner function, and it's used for when we have a function within another function. The second idea that we need here is that when we have two things that are equal to one another, that means that they are equal for every value. So for example, when I say y equals x, that means that those two things are always equal to one another. Now, if those two things are equal to one another, I can, in theory, differentiate both sides and they should have the same derivative at every point as well. So I could say that the derivative of the left-hand side is equal to the derivative of the right-hand side. I'm just doing these with respect to x, and the reason for that is that we want to, in theory, get dy dx. Now, the third thing is that when we do the derivative with respect to x of y, what we actually get is dy dx. So that left-hand side of the equation I've just written there becomes dy dx. You can think of it as a fraction despite the fact that it's not a fraction, but it's like the y multiplies into the numerator. It doesn't really though, okay? So just be aware of that. And the right-hand side, the derivative with respect to x of x, well, we know that just becomes 1. So this is the idea that we're going to use moving on through here. In these questions, differentiate using implicit differentiation. So I've got x to the 4 equals y cubed. I'm just going to differentiate both sides with respect to x. And, well, we can deal with the left-hand side without too much trouble. That becomes 4x cubed. The right-hand side, though, we have to be a little bit careful here because we've got a y cubed. So that's actually the y inside the cubed function. And, you know, we are thinking of y as a function itself. So we need to use the chain rule in order to differentiate this. And so what we do is we differentiate the y cubed normally, so it becomes 3y squared. But then we need to multiply by the derivative of the inner function in this case being y. And so the derivative of y is just dy dx. And this is our process for using implicit differentiation. The next thing that I need to do is I need to get dy dx by itself. So I'm just going to divide both sides of the equation by 3y squared. And that leaves 4x cubed on 3y squared. So the beautiful thing here is that now I have a derivative in terms of both x and y, which, you know, that's fine. I guess the only drawback is that in order to use it, we need to know both the x and y coordinates. But it does make it much nicer that, you know, we can do this when we get to questions like the next one that I have here, the x squared plus y squared equals 5. So the thing is that, yes, you can differentiate this without needing to use implicit differentiation. You can actually just rearrange the equation and rewrite it as y equals. However, that's going to be pretty nasty to do. And so the better option here is just to use implicit differentiation. So we'll do the derivative of the left-hand side equals the derivative of the right-hand side. The derivative of the left-hand side, well, the x squared just becomes 2x. The y squared, again, we've got that y inside the squared function, so it's function within a function, becomes 2y dy dx. And the derivative of a constant is just 0. So now I'm going to just rearrange this to get dy dx by itself. I've got 2y dy dx equals negative 2x. I can divide by negative 2y to get dy dx equals negative x on y. The 2's cancelling each other out. So that's quite a nice solution. Third one's going to be a little bit more tricky. We've got xy equals sine y. So For this one here, again, we'll do the derivative of both sides with respect to x. Oh, don't know what happened there. That was a bit weird. So the derivative of the left-hand side. Now we've got x multiplied by y there. So this is going to be a product rule. So the product rule is u dv dx. U in this case is just x. dv dx is the derivative of y with respect to x, which is dy dx. Plus v, which is y, multiplied by du dx, which in this case would be 1. Over on the right hand side of the equation, the derivative with respect to x of sine y. Well, again, we've got the y inside the sine function, so we'll be using chain rule here. So we differentiate normally, sine becomes cos, and we multiply by the derivative of the inner function. The thing that we need to do here now is to simplify this a little bit. So I'm going to group both of my dy dx terms on one side of the equation, and I might actually take the x dy dx over to the other side. So I've got y equals cos y dy dx minus x dy dx. I can then take out the dy dx as a common factor. So I've got cos y minus x. And then the last thing to get the dy dx by itself is to divide. So we end up with dy dx equals y over cos y minus x. We should be able to confirm this using a calculator. So I'll just bring that up. What happened there? Interesting. So here's the calculator. I've already done it here, but we'll clear all. Okay. So on the calculator there is an implicit differentiation function, and we can just start off by writing our equation. So I'll move this out of the way again so I can get it. It was xy equals sine y. And I'll just highlight that, go to interactive calculation imp diff. So we've got our function there, independent variable is x, dependent variable is y. We go okay. And well, virtually the same answer. You notice that it uses the notation y dash. That's okay, that's notation that we are familiar with. They've also got a negative out the front, but you notice that they've just taken a negative out of the denominator, so it's an equivalent answer. So, swinging back over here to the last example I'm going to look at. For the curve with equation blah, find dy dx and hence the gradient of the curve at the point 1, 3. So you notice here that they've given us both x and y coordinates. So that's something at least. Now I'm going to start off by doing derivative of both sides of the equation with respect to x. Oh, I've got another one equal to 5. That's a coincidence. So derivative of the left-hand side becomes 4x. That part's easy enough. Minus. Now I'm going to be a little bit careful with this one. I've got the 2xy there. I might even just take the 2 out the front. But that xy, it's the same derivative that we dealt with before, and I'm doing it again because it is a fairly common one, so it's a good one to kind of get used to. So u dv dx, which in this case is going to be dy dx, plus v times du dx. Okay, that's that part of it done. Then we've got the plus y squared, which becomes plus 2y dy dx. And on the right hand side, the derivative of 5 is just 0. So I can probably expand the brackets and move some stuff over to the right hand side of the equation all in one step. So I've got 4x minus y when I expand that out. And I'm going to add the 2x, so there's going to be a 2y there, but going to add the 2x dy dx to both sides. and I'm going to subtract the 2y dy dx from both sides. And then, as I did in the last question, I can take out the dy dx as a common factor. So 4x minus 2y equals dy dx out the front of 2x minus 2y, which then is just a matter of dividing by the 2x minus 2y. So dy dx equals 4x minus 2y over 2x minus 2y. I could also divide off the common factor of 2, which is going to leave us with 2x minus y over x minus y. The last part of the question is to find the gradient of the curve at the point 1, 3. So keeping in mind the gradient is dy dx. So we'll go at 1, 3. That's going to give us 2 times 1 minus 3 over 1 minus 3. And simplifying that, 2 minus 3 is negative 1. 1 minus 3 is negative 2. So the gradient is just half. I'm going to leave the video there. That's all we really need for implicit differentiation. So I'll see you again next time.